Lab 2, the motion of a falling object, in which I try to answer the question, does the drag force matter? In this lab, I had my mom drop a ping pong ball, and then I constructed two models of the motion, one with drag and one without drag. I then compared the results to each other and to the experimental data, and I found that the model with drag was the only model that correctly predicted the motion of the ball. The ball is in free fall, which means that the only forces acting on it are the weight force pulling it down and the drag force pushing it back up. The weight force is given by the equation negative mg times j hat, where m is the mass of the ball, g is the acceleration due to gravity, and j hat is the unit vector of the y-axis. The drag force is given by the equation negative b times the magnitude of the velocity squared times the unit vector of the velocity. I used the fact that any vector can be written as the product of a unit vector and the vector's magnitude to simplify this equation to negative b times the magnitude of the velocity times the velocity vector. And you will note that the drag force is positive because it opposes the velocity, which is negative, and two negative components means a positive force. In these equations, b is a small constant, but that does not necessarily mean that we can ignore the drag. In my video, I set the origin to be the center of the ball in the first frame that I was analyzing, and I set the positive y direction to be up. The ball was rather blurry as it fell, so I tracked the center of the blur as an approximation of the center of the ball. You can see that the ball speeds up as it falls, which means that the net force is in the negative y direction. With the data from Tracker and a little bit of extra research, we have enough data to initialize a computer model. I imported the ball's initial position and velocity and the initial and final time from Tracker, and I googled the mass of a ping pong ball and found that it is 2.7 grams, which is equal to 0.0027 kilograms. I also know that the acceleration due to gravity is 9.8 meters per second squared, and I am choosing to start the model off with zero drag, which means that b will be set to 0. I import those values over here, and then to track the position of the ball, I find the net force by finding the weight force and the drag force, and then adding them together, and then I use that net force when applying Newton's second law. And so when we run the model, we should see a ball dropping slowly at first and then speeding up, and we should also see arrows representing the forces in play. This one represents the weight force. This isn't quite right, however, because I'm ignoring drag in the model. To include drag, I will change b to the value that I found earlier makes the model best suit my data, and run the model again. We don't actually see anything different, though, because the drag force is so small that its arrow is not actually included in this model. However, if we look at a comparison between all three sets of data, we see that there is a difference. This graph compares the experimental data to the data from both runs of the model. We see that all three lines agree at the beginning, but the model without drag starts to overpredict the motion of the object towards the end, while the model with drag matches the data throughout. This means that the model with drag is a better fit for the data than the model without drag. Now at this point you may be wondering about the concept of terminal velocity. Terminal velocity is a constant velocity that happens when the weight force is equal to the drag force. I made this graph using the same code as before, except I told it to graph the velocity versus time instead of the position versus time, and I extended the time to 5 seconds. You can see that the acceleration, which is the slope of the line, decreases in the model with drag until it reaches 0 at the terminal velocity, while in the model without drag, the acceleration remains constant and the velocity continues to increase. Another thing to consider is if the initial velocity has any effect on the terminal velocity, and the answer is no. This graph shows the ping pong ball being dropped with 0 initial velocity and with a small negative initial velocity, and you can see that both graphs decrease to the same terminal velocity. In conclusion, the drag force does matter, It allows for terminal velocity to exist, and it can affect measurements. Thanks for watching.